Hi, Professor NTA. For the PT2 track, I would like to talk about the FE bench, a benchmark for real-time relational data feature extraction sharing. So, my name is Zhang Ziling. Also, you can call me Harry. So, first we go to agenda. I dissect the parts into six parts. So first, I'm gonna talk about what is this paper about and key findings and contributions. Then following that is prior works and the connection between this and FE bench. Then the evaluations, also what works and what is missing. Then the auto ML robustness and the concern and the counterfactual example I want to talk about. And last is the suggested improvement. So this is what I'm going to talk about. We all know the machine learning excel at finding patterns from massive amount of data sets, but the real engineering challenge arises when you try to do this production in real time. So this is where the real-time feature extraction comes into play. So it is critical stage responsible for the pulling feature from database, which is the foundation of the AI inference. To make AI model actually produce accurate predictions when data updates by new input. So what makes this paper so important that is that the author introduced the FE bench, which stands as a very first benchmark specifically designed to evaluate this RTFE system. So the author did not just use synthetic or any simulated database. Instead, they use the real world data that is highly plausible to solve the real world problem. They evaluate RTFE characteristic, which is the workload of generating new feature that use over 100 real data sets sourced from the industrial partners, such as the like the Kaggle and the UCI machine learning repository. So for those audience who are new to the machine learning space like me, those like UCL and Kaggle are essential for the industrial and research use. They provide clean, diverse, and free data set for the global research. So by leveraging those actual industry data, this paper ensures the benchmark is both comprehensive and practically useful. So overall, as I mentioned in the slide, that we're going to talk about the feature part here and the feature extraction. So this benchmark is to set a benchmark for feature extraction in a steady and fast enough way. So we're going to talk about the latency and the tail latency and concurrent performance when we extract the feature. So coming to that, I'm going to talk about the method structure and the evaluations. So some of the key finding here is that 70% of bottleneck in online machine learning pipeline work that the RTFE account for up to 70% of the execution time. And he also split into this specialized general system like OpenMLDB and the Flink. And in conclusion, the paper found that the specialized system is 100 times faster than the general system. But the trade-off is the specialized system is has suffered severe long tail latency that the latency can spike 21.8 times than the median time due to long disk writing. And so this contribution is it provides a workload analysis, standardized benchmark, the FE bench, and define a template and usable, reusable test bed as open source. And the main reason why in here, I can just give a blink that the Flink, it has some extra step for computation process. Flink run into the JVM first, then add some, extra step and open MLDB, uh, manipulate directly to the machine code. That's called LLVM. So it's much more efficient. So here's the prior works and the connection between this and the FE bench. So this research is based on the paper is called Database and Transaction Processing Performance Handbook by Jim Gray. So it has four pillars here. Uh, it has relevance, and the simplicity, portability, and scalability that it measures the performance of the kind of work real business actually do, and the test must be easy for people to understand to remain credible. And then it should be easy to implement many different types of system. And following that, the scalability is talking about the test. Well, for small and massive computer is all the same. So, so basically, the paper looks at the two main way that building the RTF system today. So this is kind of like a ruler. All right. So I'm going to talk about the methodology and the pipeline architecture. We have the workload simulator in here. And for student like me who is new to data set, this is a very cool technology instead of just loading all the data at once. The simulator replace transaction one by one. This is exactly how the real world app like Uber or credit card system work, where they react to every new events as it happens. So it basically have like data loader. It's responsible for the preloading statistic data, like user data into system. Then the workload simulator is a preload history data into the memory and replace the tuples one by one, simulate the real world coming transaction. Then it's a performance monitor. It makes sure the response time for each request, and then sorry. And it take a look at the latency. So this is how the paper measure the things. So to measure the performance, they also use the TP50, means the average, and the latency TP99 and 999. So that is the worst case. You basically can think like that. So while the TP50 tell us the average speed, the TP999 tell us the worst case scenario. So take an example. In financial safety, we care about the worst case because a slow response could allow fraud to succeed. So in this experiment, the author compared two very different systems, like we mentioned previously. The Flink, a general purpose system that is used widely in the industry, and the Open MLDB, a specialized system built specifically for speed. So the metrics used here to go beyond just, average speed, we look like the TP50, which is the median response time. But more importantly, we look at the tail latency like TP999 for the critical tasks like fraud detection. The worst 0.1% cases are often the most important. So from the chart, we can easily to see that the specialized system can outperforming general system in average request amount of time. While in R999 is will delay the response significantly. So that's the reason is I mentioned before, because the Open MLDB is nearly 100 times faster than the Flink because of the coding process that the general system directly it needs to use the JVM, where the other one don't. So let's look at the reason why it's happened. So we can look at the hardware symptoms in the figure 13. The author used the technique called TMAM, micro architecture metric analysis, to see where the CPU is struggling for a simple task. The bottleneck is the front end bound, meaning that the CPU is busy just organizing and decoding instructions. However, for complex AI query, Q3 to Q5, it becomes backend bound, which means the CPU is stuck waiting for the data to arrive from the memory. This is often caused by cache missing. So now if we look at the figure 14, we can see how the MLDB used smart planning to solve this hardware problem. Let's use Q0 as our example. Um, the window use in query 0, we need data from both 1 hour and 2 hour window. And Flink's plan reads the data twice, which creates a lot of redundant work for CPU. And uh, however, since this overlap, it reads the large 2 hours window once they reuse the data for both calculation. This directly reduces the number of instructions the CPU has processed, lowering the restricting metrics we see in the figure 13. Yeah, so in summary, these two figures provide a vital point. OpenMLDB's massive speed advantage doesn't just come from raw hardware power. It comes from working smarter at the plant level, using machine code, reusing data window, and employing specialized operators to eliminate the micro architectural bottlenecks that slow down general purpose system like Flink.